So one thing I forgot to mention is that you may be wondering why you minimize f of x. Why not maximize it or uh, optimize it in another direction? Well, it's because you can turn any problem that involves optimization into a minimization problem. For example, if you have the maximum of f of x, if you want to maximize f of x, sorry, then that's equivalent to minimizing the negative of f of x. And then with regards to these constraints down here, you may be wondering, okay, why is there a 0 on the right-hand side? Well, it's because you can always subtract anything from the right-hand side to get 0. And you may be wondering, okay, why in the inequality constraints is it only less than or equal to uh, 0? Well, it's because um, you can flip the sign by multiplying by negatives on both sides. And the sign flips because 0, when you multiply by negative, it stays the same. But this one changes. Then you may also be wondering, okay, why is it less than or equal to? Why is there an equal to? Well, it's because it has to do with active and inactive constraints in the Fritz-John conditions. So when the constraints are active, gi of x is equal to 0. That means that your equation is going to change. But then if it's just gi of x is less than 0, then you're just going to get the Lagrange multipliers method with g sub I is less than 0. You just have to like check if your minimum is in fact less than 0. But when g of I of x is equal to 0 as actives, then you get some extra terms. So hopefully that clears everything up. So it all starts with this. What is a non-empty, closed, convex set? Well, a set C, which is a subset of Rn, is convex if, for all xy as a member of C and all t within 0 to 1 inclusive, t times x plus 1 minus t times y is a member of C. So that basically means this orange line segment over here that connects x and y, the equation for that is this. And a set C is convex if within that set you can take any 2 points, connect them with this orange line segment, and all of the points on this orange line segment will be in the set as well. That's the definition. So C is closed if you have xk as a member of C and sequence xk approaches x, then x must also be a member of C. So this means that it's a really complex way of saying it, but it means basically if you start with x sub 1 all the way to x sub k, all the way to x, where x is maybe on the boundary, then x is also within C. So this means that basically all points on the boundary are within the set. That's basically it. So C is non-empty if C contains at least 1 point. Now let's smoothly transition from the concept of set convexity to that of function convexity. Specifically, we will prove a fact that must be true for all convex functions. So the epigraph of a function, phi, where phi is a mapping from Rn to R, is the set epi of phi, in which you have a pair x comma y, where x is a n-dimensional vector and y is a scalar. Therefore, they're within the member of Rn plus 1, such that scalar y is greater than or equal to phi of x. So you can imagine like a U-shaped convex graph, and the epigraph of that graph is all points above that U-shape. So phi is convex implies that the epi of phi is convex, and the epi of phi is convex implies that phi is convex. So this means that that's how we connect these concepts. And of course, we're talking about a closed, non-empty, convex set. I probably should have specified that, but you'll get the picture. So now we will take 2 points on the graph. That's also on the epigraph, x1 comma y1 and x2 comma y2, where y1 is phi of x1 and y2 is phi of x2. Therefore, if the epigraph is convex, then if x bar comma y bar is the line segment connecting, so x bar is a point on the line segment connecting x1 and x2, and y bar is a point on the line segment connecting phi of x1 and phi of x2. So t, that controls which point it actually is, and that's just the line segment. It's a member of epi of phi because it is convex, which implies that y bar is greater than or equal to phi of x bar for all t as a member of 0, 1, because, it's convex. And because y bar is greater than or equal to phi of x bar, you have this expression over here. This is y bar, this is phi of x bar. So yeah, that's the definition of convexity for an n-dimensional function. And that is it.